The National Electrical Code, or NEC, does not specifically require sleeving of a concrete encased electrode, or C, cable that is installed in a continuous run through a slab. However, NFPA 70E, which covers electrical safety in the workplace, states in section 110.11 that where outside influences can physically damage conductors and cables, protection shall be provided by mechanical protection. Furthermore, IEEE 384, which is the standard for gas-insulated substations, states in section 11.5.2.1 that where cables pass through access holes in false slabs, they shall be provided with suitable sealing and protection. This protection shall include provisions to prevent damage to the cable where the cable exits the floor slab. Many manufacturers of concrete encased electrode cables recommend sleeving for protection against physical damage. For example, Southwire recommends sleeving for concrete encased electrode cables that are installed through slabs. Although the NEC does not specifically require sleeving, it is considered best practice to install concrete encased electrode cables in a continuous run through slabs with some form of protection from physical damage. This can be achieved using sleeving, rigid conduits, or other methods. Therefore, while the NEC does not explicitly require sleeving for concrete encased electrode cables in continuous runs through slabs, NFPA 70E and manufacturers' recommendations support the use of some form of protection against physical damage. It is advisable to sleeve or otherwise protect concrete encased electrode cables in such installation. In further detail, let's look at ways to protect concrete encased electrodes as well as the reasoning behind this recommendation. Firstly, understanding the purpose of a concrete encased electrode is crucial. The concrete encased electrode serves as a grounding electrode, and it is typically a length of bare copper conductor encased within a concrete foundation or footing. Its primary function is to provide a low impedance path to earth, helping to stabilize voltage during electrical faults and protect equipment and personnel. Secondly, consider the potential for physical damage. When a concrete encased electrode cable passes through a concrete slab, it is vulnerable to physical damage from several sources. These sources can include the settling of the slab, movement of the building structure, direct impact from construction activities, and corrosion due to contact with the concrete and soil. Thirdly, assess the risk of damage without protection. Without adequate protection, the concrete encased electrode conductor can be easily damaged. A common scenario involves framing crews installing bottom plates directly over the conductor without notching them. This can cause the conductor to be pinched or even severed, compromising its effectiveness. Similarly, the settling of the concrete slab can exert pressure on the conductor, leading to damage over time. Sleeving provides a buffer against these forces, reducing the risk of damage. Fourthly, look at sleeving as a protection method. Sleeving involves encasing the concrete encased electrode conductor in a protective sleeve or conduit where it passes through the slab. This sleeve acts as a barrier, shielding the conductor from direct contact with the concrete and physical impacts. Common sleeving materials include PVC conduit, rigid metal conduit, and flexible metal conduit. Each material offers varying degrees of protection depending on the application and site conditions. Fifthly, understand the installation guidelines for sleeving. When installing sleeving, it is essential to follow best practices to ensure its effectiveness. The sleeve should extend a sufficient distance above and below the slab to provide adequate protection. It should also be securely fastened to the slab to prevent movement and maintain its position. In addition, consider sealing the ends of the sleeve to prevent moisture and debris from entering, which can cause corrosion over time. Sixthly, consider other protection methods. While sleeving is a common method, there are alternative ways to protect concrete encased electrode conductors in slab installations. One option is to use a rigid conduit to encase the conductor. Rigid conduit provides superior protection against physical damage and corrosion. Another option is to install the conductor within a larger chase or raceway, which can accommodate multiple conductors and provide additional protection. Seventhly, look at the importance of manufacturer recommendations. Many manufacturers of concrete encased electrode conductors provide specific recommendations for installation and protection. These recommendations are based on extensive testing and field experience and should be followed carefully. For example, Salfire recommends sleeving for concrete encased electrode cables that are installed through slabs to prevent damage from abrasion and impact. Following these recommendations helps ensure the long-term reliability and effectiveness of the grounding system. Eighthly, look at the NFPA 70E requirements in greater detail. NFPA 70E provides comprehensive guidance on electrical safety in the workplace. Section 110.11 specifically addresses the protection of conductors and cables from physical damage. It mandates that where outside influences can physically damage conductors and cables, protection shall be provided by enclosures, location, or other suitable means. This requirement applies to concrete encased electrode conductors and slab installations, highlighting the importance of sleeving or other protection methods. Ninthly, consider IEEE 384 guidance. IEEE 384 is a standard for gas-insulated substations but offers valuable insights into cable protection in similar applications. Section 11.52.1 states that where cables pass through access holes in floor slabs, they shall be provided with suitable sealing and protection. This protection should prevent damage to the cable where it exits the floor slab. While this standard is specifically for gas-insulated substations, its principles can be applied to concrete encased electrode conductors in other types of buildings to ensure their protection. Tenthly, weigh the economic considerations. While sleeving or other protection methods may add to the initial cost of the installation, they can save money in the long run by preventing damage and reducing the need for repairs. Damaged concrete encased electrode conductors can compromise the effectiveness of the grounding system, leading to safety hazards and equipment failures. By investing in proper protection upfront, you can avoid these costly consequences and ensure the long-term reliability of the electrical system. 11thly, understand the role of inspections. Regular inspections of concrete encased electrode conductors are essential to identify any signs of damage or deterioration. During inspections, check for signs of physical damage, corrosion, and loose connections. If any problems are found, take immediate action to repair or replace the damaged components. Proper inspection and maintenance can help extend the life of the grounding system and ensure its continued effectiveness. 12thly, consider the environmental factors. The environment in which the concrete encased electrode conductor is installed can also affect its susceptibility to damage. For example, conductors installed in damp or corrosive environments may be more prone to corrosion. In these cases, it may be necessary to use additional protection measures, such as corrosion-resistant sleeving or coatings. Similarly, conductors installed in areas with heavy traffic or construction activity may require additional protection against physical damage. 13thly, look at the impact on the grounding system. Damage to the concrete encased electrode conductor can have a significant impact on the overall effectiveness of the grounding system. A compromised grounding system can increase the risk of electrical shock, equipment damage, and fire. Therefore, it is crucial to take all necessary precautions to protect the concrete encased electrode conductor and ensure the integrity of the grounding system. 14thly, discuss the code compliance. While the NEC does not explicitly require sleeving for concrete encased electrode conductors, it does require that all electrical installations comply with the applicable codes and standards. This includes requirements for protection against physical damage and corrosion. By sleeving or otherwise protecting concrete encased electrode conductors, you can help ensure compliance with these requirements and demonstrate a commitment to electrical safety. 15thly, research the long-term benefits of protection. Protecting concrete encased electrode conductors offers numerous long-term benefits. These benefits include reduced maintenance costs, improved safety, enhanced reliability, and increased lifespan of the electrical system. By investing in proper protection, you can ensure that the grounding system continues to perform its intended function for many years to come. 16thly, weigh the risk assessment. When deciding whether to sleeve or otherwise protect concrete encased electrode conductors, it is important to conduct a thorough risk assessment. This assessment should consider the potential hazards, the likelihood of damage, and the consequences of failure. Based on the results of this assessment, you can determine the appropriate level of protection needed to mitigate the risks. 17thly, understand the specific site conditions. The specific site conditions can also influence the need for protection. For example, if the site is prone to flooding or seismic activity, additional protection measures may be necessary to protect the concrete encased electrode conductor from damage. Similarly, if the site is located in an area with high soil resistivity, it may be necessary to use multiple grounding electrodes to achieve adequate grounding performance. 18thly, look at the role of training and education. Proper training and education are essential to ensure that electrical workers understand the importance of protecting concrete encased electrode conductors. Training should cover the proper installation techniques, the potential hazards, and the best practices for protection. By investing in training and education, you can empower workers to make informed decisions and protect themselves and others from electrical hazards. 19thly, understand the continuous improvement approach. Protecting concrete encased electrode conductors should be viewed as a continuous improvement process. This means regularly evaluating the effectiveness of the protection measures and making adjustments as needed. This may involve implementing new technologies, refining installation techniques, or updating training programs. By adopting a continuous improvement approach, you can ensure that the grounding system remains effective and reliable over time. 20thly, consider the evolving standards. Electrical codes and standards are constantly evolving to reflect new technologies and best practices. It is important to stay informed about these changes and update your practices accordingly. This may involve attending industry conferences, reading technical publications, or participating in professional organizations. By staying current with the latest standards, you can ensure that your electrical installations are safe, compliant, and reliable. 21st, consider the different types of sleeving. Several types of sleeving are available for protecting concrete encased electrode conductors, each with its own advantages and disadvantages. PVC conduit is a popular choice due to its low cost, ease of installation, and resistance to corrosion. However, PVC conduit is not as strong as metal conduit and may not provide adequate protection in areas with heavy traffic or construction activity. Rigid metal conduit offers superior protection against physical damage and corrosion, but is more expensive and difficult to install than PVC conduit. Flexible metal conduit is another option that provides good protection while allowing for some flexibility in routing the conductor. 22nd, consider the importance of proper grounding techniques. Protecting concrete encased electrode conductors is just one aspect of proper grounding. It is also important to follow other best practices for grounding, such as using appropriately sized conductors, making secure connections, and testing the grounding system regularly. Proper grounding is essential to ensure the safety and reliability of the electrical system. 23rd, review the NEC articles on grounding and bonding. The National Electrical Code, or NEC, contains several articles that address grounding and bonding requirements. Article 250 covers the general requirements for grounding and bonding, including the requirements for grounding electrodes and grounding electrode conductors. It is important to be familiar with these requirements to ensure compliance with the code. 24th, consider the importance of selecting the right materials. Selecting the right materials is crucial for ensuring the long-term reliability of the grounding system. Use only high-quality materials that are designed for electrical applications. Avoid using substandard materials that may corrode or fail prematurely. When selecting materials, consider the environmental conditions and the potential for physical damage. 25th, consider the need for supplementary grounding electrodes. In some cases, a single concrete encased electrode may not provide adequate grounding performance. In these cases, it may be necessary to install supplementary grounding electrodes such as ground rods or ground plates. Supplementary grounding electrodes can help reduce the overall impedance of the grounding system and improve its effectiveness. 26. Look at the use of exothermic welding. Exothermic welding is a common method for making permanent low-resistance connections between grounding conductors. This process involves using a chemical reaction to create a molten metal that fuses the conductors together. Exothermic welds are stronger and more corrosion resistant than mechanical connections, making them ideal for grounding applications. 27th, consider the importance of proper documentation. Proper documentation is essential for maintaining an effective grounding system. Keep accurate records of all grounding system components, including the size and type of conductors, the location of grounding electrodes, and the results of grounding tests. This documentation can be useful for troubleshooting problems and for ensuring compliance with regulatory requirements. 28th, consider the impact of harmonics on grounding systems. Harmonics are electrical disturbances that can cause problems with grounding systems. Harmonics can increase the current flowing through the grounding system, leading to overheating and equipment damage. To mitigate the effects of harmonics, it may be necessary to use special grounding techniques, such as using a dedicated grounding conductor or installing a harmonic filter. 29th, consider the use of ground fault circuit interrupters. Ground fault circuit interrupters, or GFCIs, are devices that protect people from electrical shock by detecting ground faults and interrupting the circuit. GFCIs are required in many areas, such as bathrooms and kitchens, where there is a high risk of electrical shock. In addition to protecting people, GFCIs can also help protect equipment from damage caused by ground faults. 30th, consider the importance of regular testing of grounding systems. Regular testing of grounding systems is essential to ensure that they are functioning properly. Grounding tests can identify problems such as loose connections, corroded conductors, and high impedance grounds. The frequency of testing should be based on the environmental conditions and the criticality of the equipment being protected. 31st, consider the importance of protecting the concrete encased electrode conductor where it exits the concrete. Ensuring the protection of the concrete encased electrode conductor where it exits the concrete is paramount. This transition point is particularly susceptible to damage. Reinforce this area with robust sleeving or a protective enclosure. Regularly inspect this area for signs of wear, corrosion, or physical stress. Implementing these measures will significantly enhance the longevity and reliability of the grounding system. 32nd, be mindful of the soil conditions surrounding the concrete encased electrode. The composition and moisture content of the soil greatly influence the effectiveness of the electrode. Soil resistivity should be tested to determine its conductivity. Amend the soil if necessary to improve its electrical properties, ensuring a solid ground connection.